we left off last time here announcing that there are error correcting codes that don't have this massive 200% overhead of the duplication code, the simple one where we send each bit 3 times instead of just once. So the announcement was that we can get this with 11% of overhead for a reasonable block size instead of 200. I'm sure you are all curious to find out how that should work. So here it goes. The conceptual idea is we want to use parity bits, not just one, that can't be enough, but several of them. And we want to somehow use the parity bits to locate errors. If we have a single bit error, then it's basically enough to know where the bit error occurred. Then we can just reverse the flip it again, and that undoes the mistake. The only question is, how do we use parity bits in a smart way to achieve that? And that seems not quite obvious how to do. But it turns out this is entirely possible with the following setup. I'll go through this in a second. I just want to point out this one here. We cannot rely on the bit flip to occur in the data bits. It can also be one of the parity bits, and we have to live and cope with that just as well. So without further ado, and without motivating this on that side of things much more, here is essentially the solution. We use 7 bits in this example. So these are these 7 bits. But they are not allowed to be arbitrary bit patterns. We want that whenever we have 7 bits, B1 up to B7, that these checking bits, C2, C1, and C0, are all, well, 0 modulo 2, the XOR of all those bits is always 0. And how does that work? Well, the blue checking bit just takes the first 4 position and takes their parity. Remember, taking XOR, first of all, it's associative, so you can do this in any order you want, as long as you're grouping the same bits at the end. And XOR has the feature that if you XOR a certain number of bits together, the result is exactly the parity. It's 0 if the number of ones in that collection was even, and it's 1 if the number of ones was odd. So C1 does that for the first 4 bits, the highest 4 bits. C2, the green one, does it for the first 2 plus these, counting from below, it's these 2 and these 2. And then we have the magenta one, which does it for every other bit starting from the outermost. That looks like a very curious pattern. What you might already see is I wrote here some bit strings, and you might be able to figure out what the pattern with those is. But let's first of all just take this as a given. So we have 7 bits, and we enforce that certain subsets of bits have even parity. That means certain bit strings are no longer possible. A first observation, if no error occurs, if all 7 bits are correct, we can find out, we can check for this by computing the checking bits. And if these are all 0, then that's our signal. That's what we use to mean no error has occurred. And let's just observe what happens if we flip 1 bit. Let me see. I want to do an example for this first. Let's say we start with a combination of bits that has the proper parity, and then we flip, say, B3. Okay. So this one's different now. This one used to be 1, say, and now it's 0. What that means is that both the magenta and the green checking bit will also flip its parity. C2 is not affected because it only takes the blue positions here, and B3 is none of these, so there's no change in parity. But C0 and C1, they both flip to 1 because they were even before, and now we flip a single bit that must change the parity. And now notice that if you write 0, 1, 1, that is exactly writing the number 3 in binary. And if you take all the other numbers 1 through 7, then you see the colors or which checking bits a certain bit is taking part in is exactly encoding the index in binary. So that's what's also written on the slide now. In general, this holds for any of these bits. If the jth bit is flipped, that means we get if the ith bit is flipped, then we get a representation that the checking bits, the jth checking bit is 1 now, indicates a mistake if the jth bit in the binary representation of the index I is 1, the index that we flipped. Okay. And that is the essence of the Hamming code. We use this set of constraints here to enforce a certain structure on these 7 bits that allow us to find out if an error happened, and if so, where. Because whenever some mistake happens, the checking bits essentially tell us where was the bit flip. It's pretty ingenious and also quite simple. But if you start from scratch thinking about this, I find it intriguing that it's possible to do this very simple trick to find out where the mistake had happened. So the checking bits simply encode the position of the 1-bit error, and we allow 0 to signal no error. That's why the bits are numbered from 1 to 7 here conveniently, so that the 0 as a code for the checking bits can indicate no error has happened. Let's now turn this into an actual code. So far we've said there's these 7 bits, they just fall from the sky and they magically happen to satisfy these constraints. That's not how coding works. We start with some message bits and we want to add some extra bits of redundancy to turn that into an error correcting code. How can we do this for the 7-bit constraint, the constraint 7 bits that we did here? The core observation is that 4 of these bits, namely those ones, they only occur in a single checking bit, right? The magenta, blue, and green one. And that means we can define these based on the rest. So we can keep those, the bits at these indices 3, 5, 6, and 7. We can treat them as the input and then choose B4, B2, and B1 so that the checking bits are all 0. That's the idea, and it nicely works out that these are the powers of 2, so their binary representation has a single 1. That's exactly why that is the case, and you might already see how to generalize this picture, but for now we'll stick to the 4 plus 3 Hamming code, where we have 7 bits in total. 3 are used as parity bits. So the 4 remaining ones are the message. So if we start with a message of arbitrary 4 bits, we take those 4 bits and put them in order into the positions that are not powers of 2, whose index is not a power of 2. And then we compute the other, the remaining bits. So I called these here P1 to P2, P0 to P2, the parity bits. but they're really just chosen so that the C's are 0. Okay, so we have 4 different types of bits now. Just to get that picture clear, let me repeat that part. In the world above here, in the upper world, we have a 7-bit string, that's the B's, this one. And we have the checking bits, and these are just, the bits come from somewhere, and I can compute the checking bits, and then either I say, I like this code, no error occurred, or some error occurred, and I can tell you where. That's just, that's the mathematician's point of view. It's a definition, and I can say something about it, but this is not an algorithm. The bottom part, this one here, we have the D bits, that's the input, and we have the P bits, that's the output. We compute the P's from the D's shown by this formula. So we compute the parity of certain data bits. And it's just another way of saying if you take the D bits and the P bits and you interleave them as shown and treat them as the B bits, and then compute the C bits will be 0. Okay? So that's maybe a more complicated way of saying what's written here. The algorithm for encoding and Hamming codes is very simple. You take your 4 bits of the message, you put them in the right positions for the B's, and you compute the P's with that formula and put them at the remaining positions. That will automatically make your C 0. That's the encoding step. That gets from a 4-bit message, it turns into a, how can I do 7? 7-bit, into a 7-bit block, a block code. That's what you transmit over your unreliable communication channel. And that channel might flip a bit, or it might not flip a bit. And then we receive some bits and have to decode it. So that's what we will have to do next. First, we've only seen how can I produce the code. Now I have to also get back to decoding this. Okay, I forgot this last. I forgot that I have this interleaving step explicitly here. It's also in the picture. We talked about this. How can we decode this? So that's the second algorithmic part is you're given this encoding basically was from the bottom world to the top world. We got the D's, we computed the P's, and therefore we computed the B's. And now we try to go the other way around. We receive from our channel these bits, B, the 7 bits, and we don't know what happened. But we can compute C just using the formula from above and using the XORs. And then we know if C is 0, probably no error has occurred. Now, to be precise, the statement here is that no detectable error has occurred. Now, of course, that's important to note because it can happen that more than 1 bit flips. If the communication is really unreliable, we could have that situation. But no code can possibly detect if your channel completely randomly flips the bits. There's no way you can decode this. This is something you can prove. So we'll assume again that bit flips only happen rarely. So again, if C is 0, no detectable error occurred, and we'll talk at the end of this subsection a bit about what that means. What are the detectable errors? Otherwise, if your C is not 0, you know exactly which of the bits was twisted, and so you just flip that again, undo the mistake, and that's it. Then you're back to a code word that has C0, so it's a valid code for the Hamming code. And then you just have to take out the appropriate subpositions. That's the message bits from your Hamming code. That's the decoding step. It's fairly simple and fairly easy to compute. So this is an efficient algorithm. Just pointing this out because I'll come back to this question of how to decode. If you have any questions so far, that would be the right moment to ask them. We've seen how to encode, we've seen how to decode. Now I'd like to move on to discuss the properties of this error correcting code. So I'll give you a second for asking your questions. But if you don't have one, if you don't have any questions, then we'll move on. It doesn't look like you have pressing questions at the moment. So let me move on to this nice question. If you remember from the lower bound chapter, we talked about code distance. This is something, it was last week. It would have been nicer to have this in one session, then memories would have been fresher. But please head over to Slido. What I did is I just set this up as a tag cloud answer. So again, you can just freely type a number, but really the answer should be just a number. And code distance, that was this notion of Hamming distance. If you take any two code words that are valid in the code, what is the Hamming distance between those code words? And that had to do with the ability of a code to detect and correct a certain number of flip bits. I'll give you a second to answer this, but yeah, I think we should really get 20 votes before we move on, because this is an important point, and it also is a great way to connect to the maybe more theoretical lower bound section. Okay, I see answers slowly coming in. I think we can do at least 20. There were 23 votes for the opening question about the programming puzzle, which maybe I didn't leave open very long, so maybe a few people missed it, but we should be able to get 20. If you have no idea, just, I don't know, type no idea. That's also fine. You might want to go back and check the definition of code distance. That might be something I could do. Let me try that for you. But I don't want to reveal the answer. Okay, I'll really would like to see a few more results on the poll. Time to wake up, guys. If you have no idea, type no idea. That's fine. Don't be ashamed. I know it was last week when we talked about this, and this came out of the blue now. Come on, you can do this. Well, are we really so few people today? I can see you now. We've seen there's at least 17 people in the stream. So we should at least get the 17. And don't you turn off the YouTube stream now. Oh, it actually dropped to 16. I scared someone away by saying this. Okay, so let's keep it with the 16. Here are the results. And you see some peak for 3. That's good. There's also a lot of other answers. Okay, let me lock this in now. Here's the slide from last week when we discussed this. First of all, remember the distance of a code was defined like this. You take any two code words. Maybe let me make it a bit bigger. You take any two code words X and Y. So, and code words, again, is everything you can get by taking a valid message and encoding it. without any mistakes. Okay, this is all the n-bit strings you can actually get if you take if you take a message, an arbitrary message, apply the code, and don't do any mistakes yet. That's all the code words that we get. So in our Hamming code, that's you take your 4-bit message, you add the 3 parity bits, and that's it. That's your code word. Whenever C is 0, the checking bits are 0. And then what's the distance? How many bits change if you change one message bit? Well, it turns out every message bit is part of all 3 checking bits. So in general, these all change, but some might flip twice. We get the same. We get a. Okay, this is if you flip several bits in the message, you might flip only 1 bit in the parity bits, but it turns out 3 is the right answer. Okay, and it's good to have that slide here because we discussed about what the implications of a certain code distance are for the detection and correction of mistakes. So first of all, if D is 3, that means we can at most hope to detect 2-bit errors. Detect. There's no way we can detect 3-bit errors because that might have been already taking us to the next valid code word. And we can correct at most that number of bits. So if you insert 3, that works out to 1. And that's what Hamming codes promise to achieve. Okay. So let's just, for the record, put the number here. So 3 is the right answer. And well, there are many ways to work this out. Let's also recall the lower bound that we had for Hamming codes, or for general codes. We had this lower bound on how big the distance can be with a certain combination of message length and block length. So here we have 2 to the 4 different valid code words, because that's the number of messages. We have 4 bits for the message, 2 to the 4 different combinations. And we create 7-bit code words, okay? Any of these 7-bit errors is corrected towards a valid code word. If we change any of the 7 bits, then our checking bits indicate which one was flipped, and we can reverse that flip, okay? What that means for a single code word is that it covers, it is reached by 8 different 7-bit strings. When I transmit, when I receive 7 arbitrary bits, there are always 8 combinations of 7-bit strings that map to each code word. Namely 1 where the code word itself is sent, and 7 combinations of changing a single bit. Okay? Now if you multiply these two things, we have so many code words and each covers so many 7-bit strings, you obtain exactly all 7-bit strings. So Hamming codes entirely cover the 7-bit strings. It never happens that you receive a code and you think you don't know what to do with it. Whenever you receive a 7-bit string, you will correct either 1-bit error, a flip bit, or you will declare there is no error. Okay? That means we can always correct a single bit error. That's great. The distance works out to be 3. And we can briefly think about what happens to 2-bit errors. We can definitely not correct them. That's what the lower bound, the theory, already tells us. But maybe we can detect 2-bit errors. The problem here is, so if 2 bits are flipped, we definitely notice that something has happened, because the checking bits cannot be all 0 if we flipped 2 bits. But the decoder will eagerly mistake this 2-bit error as a 1-bit error from a different code word and correct that 1-bit error, taking us actually further away from the original message. So in this case, Hamming codes fall short of achieving everything that the theory predicts might be possible. They can always correct 1-bit errors, but they cannot detect 2-bit errors. They can only detect and correct 1-bit errors, that's obvious. But if 2 bits are flipped, you correct that in another direction. There is a small variation. If you add another extra bit, another parity bit for the entire block, you can actually detect all 2-bit errors, but then you also use 1 extra bit. So in a sense, you don't get both with Hamming codes. You don't get the exact coverage of the 7-bit strings of the entire space of possible bit strings, and the best possible detection. So that's just a minor remark. Our 4+3 Hamming code, this will be the variant that we discussed in detail, encoding and decoding. And this addition might be called 4+4 or 4+3+1, I don't know. This is only for your interest, but it will not play a further role in this class. Now we've seen this example of the 4+3 Hamming code. You can generalize the same recipe to larger messages or larger blocks. And the general recipe is as follows. It only ever works if your desired block length is a power of 2 minus 1. In our case, we had L equals 3, which works out to N equals 7. That's 8 minus 1. And you can generalize this code to other powers. So you can choose L. That's a parameter for you to pick. You use the L bits as parity bits as part of the making the checking constraints 0. And you use exactly those that are at a power of 2, because then their binary representation is only a single 1. And so you can define them based on the other bits. And the other bits, well, that's N minus L in the general case, all that you didn't take. And that's pretty much it. So, I mean, you generalize the checking and parity bit formulas from what I've shown. Basically, you take this binary representation of every index in your block, and for every position in the binary representation, you have 1 checking bit. So just to make this very clear, let's go back to this again. This picture here, if we have 7 bits in total, I can represent all those numbers with 3 bits in binary, or 3 digits in binary. And that means I have 3 checking constraints, 3 checking bits. And the last one takes the last bit in the binary representation. Whenever that is a 1, I include that bit into my constraint. And notice that these are all the odd numbers, because the odd numbers have a 1 in the binary representation at the last position. Then I have the next position is whenever the second bit is a 1, and that happens to be those 4 numbers. And finally, the last one for the most significant digit is the upper half of the code. And you can generalize this. If you have 15 bits instead of 7, you have a 4th position in the front. So you would use a 4th constraint for the new most significant digit. That's how you generalize this. And now we have the parameters N and L to play with. Here's my example from before. If we want this 11% overhead, what we can do is choose L equals 7. Then we can encode 64 bits. That's 1 word of memory in our usual architectures, 8 bytes. So you can encode that as 1 block together, and any single bit error in 1 word of memory is then correctable. Now, you might notice that 2 to the 7 minus 7, 2 to the 7 minus 1 minus 7 doesn't quite work out to 64. In fact, we waste a lot of bits here. because 64 is just about too big for choosing L equals 6. We could actually use the same Hamming code, could use 120 data bits, but we can just leave some of them unused and pretend they're all 0. But the important point is we use seven checking bits, 7 parity bits on top of the data. So 7 out of 64 hopefully works out to be roughly 11%. Okay. And if you want less space overhead, you just make your L bigger, and then the space overhead becomes smaller. So in summary, Hamming codes are quite simple. They're also very efficient to realize both in hardware or software. And the overhead they introduce is really, really low, especially if you make the block size a little bit bigger than the 7-bit example we've seen. Also, Hamming codes are in a certain way best possible. Well, in the coding theory literature, these are called perfect codes because they of this property that they cover exactly the entire space, and they have not just the maximal distance between code words is the minimal distance between code words is 3. It's also basically true that code words, there's no gap left. Not all code words have difference 3, but you basically have all possible code words covering the space perfectly. It's probably the best way to say it. And this is the general pattern, right? This is your message length, and this is the number of parity bits. If we want this, we cannot. So because these Hamming codes are perfect, it's not possible to go with fewer bits. You won't be able to use fewer bits for this scenario. So you cannot improve on Hamming codes if the message length is like this, the formula from here, and well, we've seen the example for 4 in detail. We've used the example with 120 bits where we just used 64 of it in the previous example with the 11-bit overhead. You can take all these other numbers. That's message lengths. And we want to correct 1-bit errors only. If these two things are what you want, then Hamming codes are the perfect solution, and there's no possibility to improve upon those. But this is a big but. If either of these conditions is not exactly describing your situation, the situation is not so clear. For example, suppose we want to protect these 64 bits and not 120 against 1-bit errors. Maybe there's a much smarter code than the Hamming code that does it with just 6 parity checks. That might be possible because for these message lengths, it doesn't nicely cover the space. The Hamming code doesn't nicely cover the space. It overlaps. And so that is a bit wasteful. And in fact, this is a fairly open research area. Designing good error-correcting codes is still a challenge that's ongoing. And there's some interesting theory behind this that I don't want to go into, but I want to just mention the main result, the gist of it. Information theory, the same thing we used with entropy in the compression chapter. There's a corresponding theory for error-correcting codes and communication over noisy channels. And the theory basically tells you if you design a code by randomly choosing code words. So you take all possible, say, 64-bit strings, and you choose a subset of those as code words and come up with some way of encoding and decoding. If you do this randomly, it almost always works out to have very good properties in the sense that your distance will be good, and you can use this as an efficient code, filling the gaps that are left by Hamming codes when the parameters don't work out so nicely. But there's a big problem with these random codes. They both basically need a full lookup table to encode and decode. For Hamming codes, we had this nice little trick that you compute a few parity checks, and then the checking bits tell you exactly where the bit flip was. You just reverse that and you're done. That was for decoding. That was very, very quick and easy. These general random codes don't have that, and it's not known how to construct in general codes that both have good distance properties and are efficient to decode. So this is where still a lot of ingenuity and tricks are used, and there's still a bit gap between the codes that we can use in practice because they're fast enough to use in practice, and the theoretical possibility. It's a large gap in that the currently used practical methods are not as good as they might be. The theory predicts there are better codes out there, but they still have to be found. With that little outlook, I want to conclude this Unit 8 on error correcting codes. We've seen a few lower bounds, a little glimpse of the theory behind this, and we've seen the Hamming codes, a very nice little example where everything works out nicely. They're clean, they're efficient, but unfortunately they only work for a small subset of the bigger task, where you want to have a code that works with a given message length and a given guarantee of how many bits you want to correct. And that is still an unsolved open problem.